Today, we are going to look at a part of the universe that defies human logic. We are journeying into the terrifying physics of absolute darkness and the horrifying limits of human perception in our own solar system. This isn't merely about a missing planet, nor is it just about the difficulty of astronomical observation. It is a cosmic reality so overwhelmingly claustrophobic that when the mathematics first revealed it, we assumed there had to be another explanation, some error in our instruments, some flaw in our reasoning. To understand its terrifying scale, consider this. A world potentially 10 times the mass of Earth could be orbiting our sun right now, less than one light day away from us, and we would be physically incapable of seeing it with our most powerful telescopes. Not because it's hiding, not because we haven't looked carefully enough, but because the photons simply die in the journey. The light itself gives up in the overwhelming darkness. By the time we finish tonight, you will comprehend the true anatomy of this phenomenon, how the inverse square law creates an impenetrable wall of darkness in our own cosmic backyard, and how we are fundamentally blind to the vast majority of our solar system. Before we drop into the void, take a second to subscribe. Now let's begin. We need to start somewhere intimate, somewhere we can touch and feel and measure with our hands, because the horror of what we're about to explore only becomes real when we build it up from human scale, step by agonizing step, until we're staring into an abyss that exists not in some distant galaxy, but right here, in the neighborhood we mistakenly believe we understand. So let's begin with light itself, not the abstract concept, the actual physical thing, the particle, the wave, the phenomenon that allows you to read these words, to see the face of someone you love, to navigate through the world without crashing into walls. Light is so fundamental to our existence that we rarely stop to consider what it actually is. We flip a switch and the darkness vanishes. We open our eyes and photons stream into our retinas, and our brain constructs reality from their arrival. It feels instant. It feels effortless. It feels permanent. But light is not permanent. Light is fragile. Every photon that exists is born in a moment of violence. An electron shifts between energy states in an atom. Nuclear fusion tears hydrogen atoms apart in the core of a star. A fire consumes wood and releases electromagnetic radiation. These are birth events, tiny explosions of energy that send photons screaming outward into whatever space happens to surround them. And from that moment of birth, every single photon is dying. Slowly, inevitably. Not through decay, like a radioactive particle, but through dilution, through the simple, merciless geometry of expanding spheres. This is where we need to slow down, because this is where the horror begins. In the mathematics of spheres, imagine you're holding a flashlight in a perfectly dark room. You click it on. Photons explode from the bulb in every direction the lens allows. Let's say for simplicity that the flashlight emits 1 trillion photons every second. 1 trillion tiny packets of electromagnetic energy, all streaming outward at the speed of light. Now you point that flashlight at a wall that is 1 meter away. The light hits the wall and illuminates a circle, a bright, clearly defined circle. You can read a book by that light. You can see the texture of the paint. The photons are densely packed, shoulder to shoulder, slamming into that square meter of wall with tremendous numerical intensity. But now, step backward. Move the flashlight to 2 meters away from the wall. The circle of light grows larger. It has to, because the photons are still traveling in straight lines, still expanding outward in a cone. And the farther they travel, the more space they have to spread into. And here is the critical point, the point where the mathematics becomes cruel. When you double the distance, you don't have the brightness. You quarter it. When you move from 1 meter to 2 meters, the light doesn't become twice as dim. It becomes 4 times as dim. This is the inverse square law. And it is not a suggestion. It is not an approximation. It is an absolute physical law that governs every single photon in the universe. Why does this happen? Because area increases with the square of radius. At 1 meter distance, those 1 trillion photons are spread across a circle with an area of roughly 3 square meters. At 2 meters, they're spread across 12 square meters, 4 times the area. Same number of photons, 4 times the dilution. At 3 meters, 9 times the area, 9 times the dilution. At 10 meters, 100 times the dilution. The photons haven't disappeared. They haven't lost energy individually. They're still traveling at the speed of light. They're still the same electromagnetic waves they were when they left the bulb. But they are now separated from each other by vast stretches of empty space. The same trillion photons that created a brilliant reading light at 1 meter are now scattered so thinly at 10 meters that the wall appears dim, murky, difficult to see. And we're still in a room. We're still talking about meters. We haven't even left the building yet. Now let's scale up. Let's take that flashlight outside. Let's point it at something 1 kilometer away. 1,000 meters. The inverse square law doesn't care about our human sense of what seems like a large distance. It simply calculates. 1,000 meters. Distance squared. 1 million. The light is now 1 million times more dilute than it was at 1 meter. Those trillion photons per second, which created a brilliant spotlight at arm's length, are now spread so catastrophically thin that they are completely invisible to the naked eye. You cannot see the spot of light on the wall 1 kilometer away. The photons are arriving. They are absolutely arriving. They are hitting the surface. But they are so scattered, so separated from each other, that they create no perceptible brightness. The signal has drowned in the noise, and we haven't even begun to talk about space yet. Let's pause here and make sure we understand what we're dealing with. Because this isn't a limitation of human eyesight. This isn't a problem with our instruments that better technology could solve. This is fundamental physics. When light travels through empty space, it dilutes according to an immutable mathematical law. Every doubling of distance quarters the intensity. Every 10 times increase in distance reduces the intensity by a factor of 100. The photons are still there. Energy is conserved. But they are spread across an ever-expanding sphere of space, becoming more and more separated, less and less dense, until the gaps between them yawn wider than continents. Now, let's go to the sun. Our sun is a furnace, a sphere of hydrogen and helium undergoing continuous nuclear fusion, converting mass into energy, radiating that energy outward in all directions as electromagnetic radiation. Photons, trillions upon trillions upon trillions of them, every microsecond, fleeing the surface at 300,000 kilometers per second. The sheer number of photons the sun emits is almost incomprehensible. In a single second, the sun radiates approximately 10 to the power of 45 photons. That's a 1 followed by 45 zeros. a number so large that if you tried to count them one per second, you would need more time than the current age of the universe multiplied by 10 billion. These photons explode outward into the solar system in a perfect sphere, expanding at the speed of light. And immediately, the inverse square law begins its work. The merciless geometry begins to dilute the storm. Earth orbits the Sun at an average distance of 150 million kilometers. We call this distance 1 astronomical unit. At this distance, the Sun appears as a brilliant disk in our sky. It illuminates our world. It powers photosynthesis. It warms the oceans. It makes life possible. The number of photons hitting every square meter of Earth's surface every second is still enormous. Approximately 10 to the power of 21 photons per square meter per second. That's why we can see. That's why plants can grow. That's why stepping from shade into direct sunlight feels like walking into a different climate. But let's do the mathematics. The Sun is emitting 10 to the power of 45 photons per second. Earth, at 1 astronomical unit, receives about 1 billionth of that total emission. 1 billionth. Because those photons are spread across a sphere with a radius of 150 million kilometers, and Earth is just a tiny dot on that sphere, intercepting only the photons that happen to be traveling in exactly the right direction to hit it. Now let's move outward. Let's travel to Mars. Mars orbits at roughly 1.5 astronomical units, not much farther than Earth in the grand scheme of the solar system. Just 50% more distance. But the inverse square law doesn't care about percentages. It cares about the square. 1.5 squared is 2.25. Mars receives less than half the sunlight that Earth does. The Sun appears smaller, dimmer. The Martian surface is a colder, darker place, not because Mars did anything wrong, but because it stands farther from the source, and the photons have had more space to dilute. Let's keep going. Jupiter. 5 astronomical units from the Sun. Distance squared, 25. Jupiter receives 1/25 the sunlight that Earth does. The Sun from Jupiter looks smaller, noticeably smaller. If you were standing on one of Jupiter's moons, the Sun would appear as a very bright star, but not the overwhelming disk we see from Earth. Saturn. 10 astronomical units, 1% of Earth's sunlight. The Sun is now genuinely small in the sky. A brilliant point, yes. Still the brightest object by far, but no longer a disk that fills your vision. Uranus. 20 astronomical units, 1/400th of Earth's sunlight. The Sun has become a distant spotlight. Neptune. 30 astronomical units, 1/900th of Earth's sunlight. We are now so far from the Sun that the light, while still present, while still detectable, has become thin, stretched, weak, and we haven't even left the planetary solar system yet. We're still well within the region where we know planets orbit. Neptune is not the edge. Neptune is barely the beginning, because somewhere out there, somewhere beyond Neptune in the freezing darkness of the outer solar system, there might be something else. Something massive, something real, something we cannot see. We call it Planet 9. And the reason we cannot see it has everything to do with the nightmare we've been building. Let's establish what we think we know. The evidence for Planet 9 doesn't come from seeing it. The evidence comes from mathematics, from the orbits of distant objects in the Kuiper Belt, behaving in ways that seem statistically improbable unless something massive is pulling on them. These objects, small icy worlds far beyond Neptune, have orbits that cluster together in peculiar ways. Their perihelions, the points where they come closest to the Sun, seem to point in similar directions. Their orbital planes seem to tilt in similar ways. This could be coincidence, random chance. The universe is under no obligation to make sense to us. But when we run the simulations, when we model the gravitational dynamics of the outer solar system, one explanation keeps appearing as the most elegant solution. There is another planet out there, a world somewhere between 5 and 10 times the mass of Earth, a super-Earth or a small ice giant, orbiting the Sun at a staggering distance. Estimates place it somewhere between 400 and 800 astronomical units from the Sun. Some models suggest it could be even farther, 1,000 astronomical units, perhaps more. Let's use the middle estimate, 600 astronomical units, 600 times the distance from the Earth to the Sun, 90 billion kilometers, 90,000 million meters. A distance so large that light itself, traveling at 300,000 kilometers per second, takes more than 3 days to cross it. And here is where the horror begins to crystallize, because we need to understand what it means to see a planet. Planets do not generate their own light, not visible light anyway. They are not stars. They are not burning. They are rocks and ice and gas, held together by gravity, orbiting a star the way a moth circles a flame. The only reason we can see planets at all is because they reflect sunlight. Photons leave the Sun, travel across space, strike the planet's surface, bounce off, and travel back toward our eyes or our telescopes. That's it. That's the entire mechanism. Reflected sunlight. So to see Planet 9, we need photons to make a round trip, from the Sun to the planet, then from the planet back to Earth. And the inverse square law applies to both legs of the journey. Let's trace a single photon's nightmare voyage. It begins at the Sun. Born in the chaos of nuclear fusion, it fights its way up through hundreds of thousands of kilometers of dense stellar plasma, scattering and bouncing and being absorbed and re-emitted countless times until, finally, after potentially hundreds of thousands of years of struggling upward through the Sun's interior, it reaches the surface, the photosphere, and it breaks free. It is finally free. It begins traveling outward at the speed of light, 1 photon among 10 to the power of 45 siblings born in the same second, all fleeing in a perfect expanding sphere. It passes Mercury in 3 minutes, Venus in 6, Earth in 8. It is already beginning to thin out, to dilute. But there are still so many photons, such an overwhelming storm of light, that the dilution is barely noticeable. Mars in 12 minutes, the asteroid belt, it keeps going. Jupiter in 43 minutes. The photon has now been traveling for nearly an hour. It has crossed 778 million kilometers. But this is nothing. This is the warm, bright inner solar system. This is the easy part. Saturn in an hour and 20 minutes. The light is noticeably thinner now, weaker, but still present. Uranus in 2 hours and 40 minutes. Neptune in 4 hours and 10 minutes. The photon has been traveling for 4 hours. It has crossed 4.5 billion kilometers, and it has only just reached the edge of what we traditionally think of as the planetary solar system. But it doesn't stop. Because Planet 9 is not at Neptune, Planet 9 is unimaginably farther. Our photon continues. out past Neptune, into the Kuiper Belt, past Pluto, which at its farthest reaches only 49 astronomical units, past the scattered disk objects, past Eris and Makemake and Haumea. It keeps going. The sunlight here is no longer sunlight in any sense that we would recognize. The sun has become a distant point. The photon is alone now in a way that is difficult to conceptualize. The gaps between photons have grown vast. If you could somehow visualize the density of sunlight at this distance, you would see individual photons as isolated points in an ocean of empty space, each one separated from its neighbors by kilometers. 10 hours, 20 hours, 30 hours. The photon has been traveling for more than a day. It has crossed 25 billion kilometers. It is farther from the sun than any human-made object has ever traveled. And it still has so far to go. 40 hours, 50 hours, 60 hours, 2.5 days. The photon is now in a region of space so dark, so utterly devoid of light, that if you were somehow transported there, even with your eyes fully adapted to darkness, you would see nothing. Not blackness, not shadow, nothing. The human eye requires a certain minimum number of photons to register any signal at all. At this distance from the sun, that threshold is not being met. Darkness is the default state. Light is the rare exception. And finally, after more than 3 days of continuous travel at the speed of light, after crossing 90 billion kilometers of empty space, the photon arrives at Planet 9. It arrives exhausted in a sense. Not physically exhausted, photons don't tire, but statistically exhausted. Diluted beyond recognition. Remember, the inverse square law has been working the entire journey. At 600 astronomical units, the intensity of sunlight is not 600 times weaker than at Earth. It is 600 squared times weaker, 360,000 times weaker. The brilliant sun that illuminates our world and makes our shadows sharp and fills our eyes with light has become something else entirely at this distance. A bright star, yes, the brightest star in the sky by a tremendous margin, but a star nonetheless, a point of light. And now our photon, having survived this immense journey, having beaten the statistical odds simply by being one of the few that happened to be traveling in exactly the right direction to reach this distant world, now it must interact with the surface. What is Planet 9 made of? We don't know. We've never seen it. But we can make educated guesses based on what we know about planetary formation and composition at this distance from the sun. It is almost certainly an ice giant or a rocky super-Earth covered in a thick layer of frozen volatiles. Methane ice, nitrogen ice, water ice, carbon dioxide ice, ammonia ice. These are not the shimmering crystalline ices of Earth. These are ices that have never known warmth, never experienced a thaw. They formed in the freezing darkness of the outer solar system billions of years ago, and they have remained frozen ever since. They are cold in a way that is difficult to comprehend. Not the cold of Antarctica, not the cold of liquid nitrogen. We're talking about temperatures potentially as low as 30 or 40 degrees above absolute zero. 30 Kelvin, 40 Kelvin. At these temperatures, atoms barely vibrate. Molecules are locked in rigid crystalline structures. Matter itself becomes sluggish. And these ancient, frozen surfaces are black. Not metaphorically black, not dark gray or dark blue. Black. Because ice at these temperatures doesn't reflect light the way ice on Earth does. Fresh snow on Earth appears brilliant white because it is full of tiny crystal structures and air gaps that scatter light in all directions. But ice that has sat undisturbed for billions of years in the radiation-soaked environment of deep space becomes something else. Cosmic rays and solar wind particles and micrometeorites slowly damage the crystalline structure. They break molecular bonds. They create complex carbon compounds, tholins, organic molecules that are dark red or brown or black. The surface of a world like Planet 9 would likely have an albedo, a reflectivity of perhaps 10 to 20%, maybe less. 80 to 90% of the photons that strike it are absorbed, swallowed, converted into a tiny, imperceptible amount of heat that is immediately radiated away as infrared. So our photon, having traveled for 3 days, having crossed 90 billion kilometers, strikes this ancient frozen surface, and there is a 90% chance it is simply absorbed. Its journey ends. The electromagnetic energy is converted to thermal energy, and then radiated away into space as infrared photons that disperse into the void. But let's say our photon is lucky. Let's say it strikes a patch of slightly higher albedo ice, a region where the surface is still relatively clean, and it reflects. It bounces off. It begins the return journey. And now the nightmare repeats in reverse. The photon leaves Planet 9, traveling back toward the inner solar system at the speed of light. And immediately, the inverse square law begins working again. Because reflected light also dilutes, also spreads across an expanding sphere. The photon is once again alone in the darkness, separated from any other reflected photons by vast distances, traveling through an empty void that cares nothing for its existence. 3 days later, it reaches Earth's orbital distance from the Sun, but Earth is not necessarily there. Earth is a moving target, a planet hurtling through space at 30 kilometers per second. For a photon reflected from Planet 9 to actually hit Earth, to actually enter our telescopes, it must not only survive the round-trip journey, it must also be traveling in exactly the right direction to intersect Earth's position at exactly the right time. The odds of this are fantastically small. But let's say, once again, we're lucky. Let's say this photon, against all odds, is traveling in exactly the right direction. It crosses the orbit of Neptune, Uranus, Saturn, Jupiter, the asteroid belt, Mars, and finally, after more than 6 days of total travel time, after bouncing off a frozen world 90 billion kilometers away, it arrives at Earth. And here is the final horror, the final crushing weight of the mathematics. That photon hits the mirror of our telescope, and it is alone, completely, utterly alone, because of the inverse square law applied twice, once on the way out, once on the way back. The intensity of the reflected light has decreased by the distance to Planet 9 to the 4th power. Not squared, 4th power. 600 astronomical units to the 4th power is approximately 130 billion. One photon out of every 130 billion photons that left the Sun and had a chance of hitting Planet 9 and reflecting back to Earth actually makes the journey. Let me put that in perspective. The Sun emits about 10 to the power of 45 photons per second. Planet 9, at 600 astronomical units, intercepts an infinitesimally small fraction of those photons. Of the photons that do hit Planet 9, about 10 to 20% reflect. Of the reflected photons, an infinitesimally small fraction happen to be traveling in the right direction to eventually hit Earth. And of those, we need to collect enough in our telescopes to create a detectable signal above the background noise of the universe. The mathematics are brutal, absolutely brutal. Even with our most powerful telescopes, even with instruments that can detect light sources millions of times fainter than the human eye can see, Planet 9 would appear as an extraordinarily dim object. Perhaps magnitude 24 or 25 on the astronomical brightness scale. For context, the faintest stars you can see with your naked eye on a perfectly dark night are around magnitude 6. Every increase of 5 magnitudes represents a 100-fold decrease in brightness. Planet 9 would be roughly 100,000 times fainter than the faintest star you've ever seen without a telescope. And it's moving, slowly, because objects in distant orbits move slowly. Planet 9 might take 10,000 to 20,000 years to complete a single orbit around the Sun. From our perspective, it would drift across the sky at an agonizingly slow pace, a few arc-seconds per year. Searching for it requires taking images of vast swaths of the sky, then returning months or years later to take the same images again and look for anything that has moved. It requires sifting through millions of points of light, most of which are distant galaxies or asteroids or image artifacts or cosmic rays hitting the detector, and trying to find the one point that moves in a way consistent with a distant planet. We are looking for a needle in a haystack where the needle is invisible and the haystack is the size of the sky. And here's what makes this even more terrifying. We might be looking in the wrong place, because all of our estimates about where Planet 9 might be located are based on indirect evidence, on the clustering of distant Kuiper Belt object orbits, on computer simulations, on statistical analyses. We don't actually know where it is. We have a search region that covers potentially thousands of square degrees of sky, and we have to search all of it, carefully, repeatedly, hoping that our instruments are sensitive enough, hoping that the planet is reflective enough, hoping that we happen to be looking at the right patch of sky at the right time when it happens to be near its brightest point in its orbit. It could be anywhere in that vast search region. It could be at perihelion, its closest approach to the Sun, perhaps 400 astronomical units away. Or it could be at aphelion, its most distant point, potentially 800 or even 1,000 astronomical units away. At 1,000 astronomical units, the inverse square law becomes even more punishing. The reflected light would be nearly 7 times fainter than at 600 astronomical units. 7 times fewer photons reaching our telescopes. 7 times closer to being completely invisible. There is a distance, some finite number of astronomical units, beyond which a planet of a given size and albedo simply cannot be detected with current technology. It's not a soft boundary. It's not a gradient where things gradually become harder to see. It's a cliff, a hard cutoff where the signal drops below the noise floor and detection becomes impossible no matter how long you stare. We don't know exactly where that boundary is for Planet 9, but we know it exists. And we know we might be dancing right on the edge of it. This is the illusion of light. The comfortable assumption that if something is large enough, massive enough, close enough, we should be able to see it. But mass and visibility are not the same thing. Planet 9 could be 10 times the mass of Earth. It could have a powerful gravitational field that dominates the dynamics of distant Kuiper Belt objects. It could be shepherding orbits, clearing gaps, acting as a gravitational anchor for an entire region of the solar system. And yet, it could be completely, utterly invisible to us. Not because it's hiding behind something, not because it's in some exotic state of matter, but because the photons simply cannot make the journey. The light dies in transit. The darkness wins. We are sitting around a campfire, and the campfire is the sun. And we have convinced ourselves that we can see the entire campsite because we can see the nearby rocks and trees illuminated by the firelight. We have mapped the inner solar system with exquisite precision. We know where every major planet is. We can predict their positions centuries into the future. We have sent spacecraft to every classical planet. We have orbited them, landed on them, analyzed their atmospheres and surfaces and magnetic fields. We understand the architecture of the inner solar system. But the light from our campfire only extends so far. And beyond that sphere of illumination, beyond the reach of reflected sunlight, there is darkness. True, absolute darkness. A darkness so complete that entire worlds could exist there and we would never know. Not without going there. Not without sending a spacecraft on a decades-long journey into the outer dark and hoping it happens to pass close enough to see something. And this isn't theoretical. This isn't speculation about other star systems or distant galaxies. This is our solar system, our cosmic neighborhood, the space that contains our sun and our planets and our asteroid belts and our comets. We like to think we know this space. We give it a name, the solar system, as if it's a known quantity, a mapped territory, a finished chapter. But we don't know it. We know the parts that are close enough and bright enough to see. We know the parts that the sunlight can still reach with enough intensity to reflect back to us. But the vast majority of our solar system, the overwhelming majority of the space that is gravitationally bound to our sun, exists in darkness. Permanent, impenetrable darkness. And we are blind to it. The Oort cloud, the theoretical shell of icy objects that surrounds our solar system, at distances of 10,000 to 100,000 astronomical units, is completely invisible. We have never seen a single Oort cloud object while it remains in the Oort cloud. We only see them when they fall inward and become comets. When they enter the inner solar system where the sunlight is strong enough to vaporize their ices and create visible tails. The entire outer architecture of our solar system is invisible to us. We know it must be there because we can infer its existence from the comets that occasionally fall inward. But we cannot see it. The light doesn't reach that far, or if it does, it doesn't return. Planet 9, if it exists, would be somewhere in the middle of this terrifying range. Closer than the Oort cloud, but so much farther than Neptune that the distinction barely matters. It would be a world existing in near total darkness. The sun from Planet 9's surface would appear as a bright star, but it would provide essentially no warmth and almost no illumination. The surface temperature would be determined almost entirely by the planet's internal heat, the leftover warmth from its formation billions of years ago, slowly leaking out into space. During its day, if it has something we could recognize as day, the sun would rise and set, but the change in brightness would be subtle, difficult to notice, like the difference between twilight and deep twilight on Earth. And yet this world, if it exists, is still part of our solar system, still orbiting the same star that we orbit. still bound by the same gravity that keeps Earth in its comfortable, warm, life-sustaining orbit. We are siblings in a sense, products of the same stellar nursery, formed from the same disk of gas and dust that collapsed to create the sun. But we are separated by an abyss of darkness so profound that we might never see each other. Now, let's talk about how humanity came to realize this terrifying truth. Because this understanding didn't come all at once. It came slowly, painfully, through a series of observations and calculations and failed searches that gradually forced us to confront the limitations of our perception. When we first began studying the solar system in the early days of telescopic astronomy, we assumed that we could see everything important. The classical planets, Mercury through Saturn, were all visible to the naked eye. They had been known since antiquity. When the telescope was invented, it didn't reveal new types of objects so much as it revealed details of objects we already knew existed. Mountains on the moon, phases of Venus, rings around Saturn, moons orbiting Jupiter. The first true shock came with the discovery of Uranus, a planet invisible to the naked eye, a planet that had been staring at humanity for all of recorded history, and we had simply never noticed it because it was too dim. This was the first hint that our solar system might be larger than we thought, that there might be entire worlds lurking in the darkness just beyond the range of unaided human vision. Then came Neptune, discovered not by accident, but by mathematics. Astronomers noticed that Uranus wasn't moving quite the way it should. Its orbit was being perturbed by something massive, something pulling on it with gravitational force. And so they calculated where that something should be, pointed their telescopes at that region of the sky, and there it was. Neptune, another ice giant, even farther, even dimmer, invisible without a telescope, but predictable through the language of gravity. This was a triumph, a vindication of Newtonian mechanics. The universe follows mathematical laws, and if we're clever enough, we can use those laws to predict things we cannot see. It gave us hope. It suggested that even if a planet was too dim to detect directly, we could find it by watching how it influenced the things we could see. And so the search began for Planet X, another world beyond Neptune, another ice giant that might be perturbing the orbits of Uranus and Neptune in ways we hadn't yet accounted for. Astronomers spent decades searching, taking photographic plates of the sky, comparing them, looking for anything that moved against the background stars. And they found Pluto, a small, icy world far beyond Neptune. Tiny, much smaller than Earth. So small that it couldn't possibly be the Planet X they were looking for. It didn't have nearly enough mass to perturb the orbits of the gas giants. But it was there, another object in the outer solar system. And its discovery raised a troubling question. If there's one small, icy world out there, how many others are there that we haven't found yet? The answer, we now know, is thousands. Tens of thousands. Possibly millions. The Kuiper Belt is full of small, icy bodies, remnants from the formation of the solar system, orbiting in the cold darkness beyond Neptune. We've discovered thousands of them now. We've mapped their orbits. We've sent a spacecraft, New Horizons, to fly past Pluto and see it up close. And what we found was a world far more complex and geologically active than we expected. A world with nitrogen glaciers and water ice mountains and a thin atmosphere that freezes and falls as snow during the long winter of its orbit. But here's the problem. We can only see the Kuiper belt objects that are close enough and large enough and reflective enough to show up in our surveys. We're looking at the brightest tip of a vast iceberg. For every Kuiper belt object we've discovered, there are likely hundreds or thousands that are too small or too dark or too distant to detect. We are seeing a biased sample. The universe is showing us only what we have the technology to see. And then, in the early years of the 21st century, something strange began to emerge from the data. A handful of distant Kuiper belt objects, orbiting far beyond Neptune, seemed to have peculiar orbits. Their perihelions, the points where they came closest to the Sun, were clustered together in space. Their orbital planes were tilted in similar directions. The probability of this happening by random chance seemed low. Not impossible, but low. At first, this was met with skepticism. Clustering patterns in small datasets can be misleading. We see patterns everywhere, even in random noise. Our brains are hardwired to find connections, to see order in chaos. And a handful of objects is a very small dataset. Maybe it was just coincidence. Maybe we were seeing patterns that weren't really there. But more objects were discovered, more distant, highly elliptical orbits, and the clustering persisted. It didn't go away as the dataset grew. If anything, it became more pronounced. The statistics became harder to ignore. Something seemed to be shepherding these orbits, something massive, something with enough gravitational influence to shape the distribution of objects in the outer solar system. Computer simulations were run, thousands of them, millions of them, testing different scenarios. What if there was no additional planet? What if the clustering was just a selection bias from the way we search the sky? The simulations suggested that yes, selection bias could explain some of the clustering, but not all of it. There seemed to be a real signal hidden in the noise. Then the simulations asked, what if there is another planet? What mass would it need to be? What orbit would it need to have? And the answer that kept emerging from the models was consistent. A planet somewhere between 5 and 10 Earth masses. An orbit with a semi-major axis between 400 and 800 astronomical units. A highly elliptical orbit, tilted relative to the plane of the classical planets. And if such a planet existed, it would naturally create the orbital clustering pattern we were seeing in the distant Kuiper belt. This was not proof. This was not a detection. This was a hypothesis. An explanation that fit the data better than the null hypothesis of random chance. But fitting the data is not the same as being correct. History is full of scientific ideas that seem to fit the data until better data came along and revealed them to be wrong. And so the search intensified. Telescopes around the world began dedicating time to searching for Planet 9. Surveys were conducted. Vast regions of the sky were photographed, then rephotographed months or years later. Image processing algorithms were developed to automatically identify objects that moved between exposures. Citizen science projects were launched, enlisting thousands of volunteers to visually inspect images that the algorithms flagged as potentially interesting. And nothing was found. Year after year, survey after survey, nothing. This is when the horror of the inverse square law began to sink in, when astronomers started doing the detailed calculations of just how faint Planet 9 might be. When they realized that a 10 Earth mass planet at 600 astronomical units, with a reasonable albedo, would be right at the edge of detectability for current wide-field survey telescopes. Maybe just over the edge, maybe just too faint to show up in the surveys that had been conducted so far. Deeper surveys were needed, longer exposure times, more sensitive detectors. Surveys that covered larger areas of the sky with sufficient depth to detect even the faintest possible signature of Planet 9. And these surveys are ongoing. Right now, as you listen to this, there are telescopes photographing the sky, collecting photons, building up signal, searching for a faint point of light that moves ever so slightly against the background stars. But there's a creeping realization setting in, a growing understanding that we might be searching for something that is fundamentally beyond our ability to detect. Not because we lack the intelligence or the dedication or the technology, but because the universe itself, through the simple mathematics of inverse square dilution, has rendered it invisible. If Planet 9 is at the far end of its orbit, at aphelion, it might be unreachable. Not unreachable in the sense that we could never send a spacecraft there, although that would take decades or centuries with current propulsion technology. Unreachable in the sense that the photons cannot complete the round-trip journey with sufficient density to create a detectable signal. The darkness is too deep. The distance is too great. The light simply dies. And this raises an existential question that we're only now beginning to grapple with. How much of our solar system is invisible to us? How many worlds could be lurking in the outer dark, beyond the reach of reflected sunlight, gravitationally bound to our sun but optically undetectable? Planet 9 might not be alone. There could be Planet 10, Planet 11, an entire population of super-Earths and ice giants in highly elliptical orbits, all of them too distant and too dark to see. We would only discover them if they happened to perturb the orbits of objects we can see in measurable ways, or if we got extraordinarily lucky and one of them happened to pass in front of a background star, briefly blocking its light in a way we could detect, or if we developed fundamentally new detection methods. Infrared surveys, perhaps, looking for the faint heat signature of these worlds rather than their reflected light. But even in infrared, the inverse square law still applies. Heat radiates outward in all directions, diluting as it travels, becoming fainter and fainter until it merges with the background noise of the universe. This is the blind spot of Planet 9. The claustrophobic realization that we are surrounded by darkness, that our solar system, the cosmic neighborhood we thought we understood, is mostly invisible to us. We live in a tiny bubble of light, a sphere perhaps 50 or 100 astronomical units in radius where reflected sunlight is still bright enough to see clearly. Beyond that bubble, the darkness becomes overwhelming. Objects fade into shadow. Entire worlds become ghosts. And somewhere out there, perhaps 600 astronomical units away, perhaps farther, there might be a world. A massive, ancient world. A planet that formed when our solar system was young, that has been orbiting in the freezing darkness for 4.5 billion years. Utterly alone, utterly invisible, waiting for the day when our technology finally advances enough to see it. Or perhaps never being seen at all. Perhaps existing forever in the dark, a permanent blind spot. A world that we know must be there through mathematics and inference but can never directly observe. We are sitting around our campfire, and just beyond the light, in the impenetrable darkness, there is something massive moving, something real, something gravitationally significant, but we cannot see it. The photons give up before they return to us, and we are left with nothing but orbital perturbations and computer simulations and the growing, uncomfortable realization that we do not understand our own cosmic backyard nearly as well as we thought we did. The light has failed us. The darkness has won. And Planet 9, if it exists, remains invisible. Let's conduct a thought experiment. A journey of pure imagination grounded in the hard mathematics we've already explored. We're going to place ourselves somewhere we can never physically go. Not in our lifetimes, not in many lifetimes. We're going to stand on the surface of Planet 9, and we're going to experience, in excruciating detail, what it means to exist in a place where light has almost completely abandoned the universe. Close your eyes for a moment. Not literally, of course, because you're listening to this, but close them in your mind. Imagine that you are standing on a surface, not the warm, familiar surface of Earth, not stone warmed by sunlight or sand cooled by evening breeze. This is something else entirely. You're standing on a plane of nitrogen ice, frozen nitrogen, the same gas that makes up 78% of Earth's atmosphere. But here, at 35 degrees above absolute zero, it is solid. It is hard beneath your feet, harder than concrete, harder than steel at room temperature. Because at these temperatures, matter itself becomes different. The molecules are locked in crystalline matrices so rigid that they barely vibrate. If you could somehow strike this surface with a hammer, it would ring like metal. A pure, clear tone that would propagate through the ice and fade into silence. The horizon stretches out before you, flat, featureless, a plain of white nitrogen ice extending in all directions until it curves away beneath the horizon. But you cannot see much of it, because it is dark here, profoundly, overwhelmingly dark. Your eyes, even if they were perfectly adapted to darkness, even if you had spent years in absolute blackness, allowing your rhodopsin to build up to maximum sensitivity, would struggle to perceive anything. There is light. Technically, mathematically, photons are arriving from the sun, but they are so sparse, so separated from each other in time and space, that they create almost no perception of brightness. Let's quantify this darkness. At Earth, on a clear day, approximately 10 to the power of 21 photons hit every square meter every second. That's the number we mentioned earlier, a trillion photons. Your retina, which has an area of about 1,000 square millimeters, receives roughly 10 to the power of 18 photons per second when you look at a sunlit scene. That's why you can see. That's why colors are vivid and edges are sharp and shadows are defined. Here on Planet 9, at 600 astronomical units from the Sun, the number of photons hitting each square meter each second has decreased by a factor of 360,000. Instead of 10 to the power of 21 photons, you receive approximately 3 times 10 to the power of 15 photons per square meter per second. That sounds like a lot. It's still trillions of photons. But spread across a square meter, arriving at random intervals, it creates a light level roughly equivalent to starlight on Earth. Not moonlight. Starlight. The faint illumination you get on a moonless night in a location far from any city lights, where the only sources of light are the distant stars. Except it's worse than that. Because on Earth, when you're under a clear, moonless, starlit sky, You're receiving light from thousands of stars simultaneously, each one contributing its photons. They add up. They create a faint, diffuse glow that allows your dark, adapted eyes to barely perceive your surroundings. Here, on Planet 9, there is only one star that matters, our Sun. And it is not a diffuse glow. It is a point source, a single bright star in the sky. Brighter than any other star by a factor of thousands, yes, but still a star, still a point. You look up. The sky above you is full of stars, thousands of them, tens of thousands. Because there is no atmosphere here to scatter light, no air glow, no light pollution. The stars are sharp, unblinking points of light scattered across a perfectly black sky. And among them, in one particular direction, there is a star that is brighter than all the others. The Sun, our Sun, your Sun, the furnace that powers all life on Earth, the gravitational anchor of the solar system, the source of warmth and light and energy. From here it appears as a star of magnitude -18, extraordinarily bright by stellar standards. If you were to compare it to Sirius, the brightest star in Earth's night sky, the Sun from here would be about 25,000 times brighter. But Sirius does not warm you. Sirius does not light your way. And neither does the Sun from this distance. You hold your hand up in front of your face. Can you see it? Barely. Maybe. If you wait long enough for your eyes to adapt, if you hold perfectly still, you might perceive a shadow. A slightly darker region against the already dark sky. But there is no detail. You cannot see your fingers. You cannot see the lines on your palm. Your hand is a void, an absence of stars. That's all. The landscape around you is similarly invisible. You know intellectually that you are standing on a plane. You can feel the solidity beneath your feet, but you cannot see it. The nitrogen ice reflects perhaps 10% of the photons that strike it. 10% of almost nothing is functionally nothing. The surface absorbs the rest, converting them into heat. But heat at this scale is meaningless. Each absorbed photon raises the temperature of a handful of molecules by an imperceptible amount. And that energy is immediately radiated away as infrared photons that disperse into space. You take a step forward, carefully, because you cannot see where you are going. Your foot comes down on the ice and there is no sound. There is no atmosphere to carry sound. Or rather, there is an atmosphere, a thin envelope of nitrogen and methane gas. But it is so tenuous, so vanishingly thin, that sound barely propagates. If you could somehow shout, the sound waves would travel a few meters and fade into nothing. You are alone in silence, surrounded by darkness, standing on a world that exists at the very edge of visibility. How long would you have to stand here, perfectly still, collecting photons with your eyes, before you accumulated enough signal to perceive your surroundings? Minutes? Hours? Days? The human eye can detect a single photon under ideal conditions. Individual rod cells in your retina can fire when struck by a single photon. But the brain requires multiple rod cells to fire in a correlated pattern before it registers a conscious perception of light. You need somewhere between 5 and 10 photons hitting nearby rod cells within a short time window to perceive a flash of light. And to perceive a scene, to build up a mental image of your surroundings, you need millions of photons arriving in a structured pattern that your visual cortex can interpret. At this light level, your eyes would be receiving photons at a rate sufficient to trigger perhaps a few scattered rod cells per second. Random firing, uncorrelated. Your brain would filter it out as noise. You would perceive nothing. Absolute darkness. Not the darkness of a closed room that your eyes eventually adjust to. Not the darkness of a cave deep underground where the faintest suggestion of reflected light eventually becomes visible. True darkness. Permanent darkness. You could stand here for hours, for days, and your perception would not change. The photons are simply too sparse. And yet, if you brought a camera, a modern digital camera with a sensitive sensor, and you mounted it on a tripod and you opened the shutter for a long exposure, hours long, the camera would see things you cannot. It would collect photons patiently, accumulating them in the pixels of its sensor, building up signal over time, and eventually, after enough exposure time, an image would emerge. A faint, grainy, noisy image, but an image nonetheless. The plain of nitrogen ice, the distant hills, if there are hills, the sun, now a brilliant point that has saturated its pixel and created a small bloom of light. The stars, trailing across the sky if the camera wasn't tracking their motion. The universe is not truly dark. It is only dark to us, to our biology, to our limited human perception. But we're not done with this thought experiment, because we've only considered the sun. We haven't thought about Earth, about home, about the world you came from, assuming this is a journey and not a permanent exile. Earth is also orbiting the sun, likely somewhere between 500 and 700 astronomical units away from where you stand, depending on where Planet 9 is in its orbit and where Earth is in its orbit. At this distance, Earth is completely invisible, not difficult to see, not challenging to detect. Invisible. There is no telescope you could carry with you that would show you Earth from here. The Hubble Space Telescope, in orbit around Earth, can detect galaxies billions of light years away. But it could not see Earth from Planet 9's surface. Because galaxies, despite being unimaginably distant, are enormous. They contain hundreds of billions of stars. They emit staggering amounts of light. Earth is tiny, a pale blue dot barely larger than a pixel even from the distance of Neptune. From here, it is nothing, lost in the glare of the sun. You could calculate where Earth should be. You could use orbital mechanics to predict its position relative to the sun at any given time. You could point your camera at exactly the right spot in the sky, and you would capture nothing. Just stars. The same stars you'd see if you pointed the camera anywhere else. Earth would be there, in the frame, but it would be buried in the noise. Too small, too dim, too close to the sun's glare to separate. This is the isolation. This is what it means to exist in the outer solar system. You're still gravitationally bound to the sun. You're still part of the same system, the same family of objects. But you are so far away, so utterly separated by distance, that even light, traveling at 300,000 kilometers per second, cannot bridge the gap in a meaningful way. Information takes 3 days to travel from the sun to where you stand. If you had a radio transmitter powerful enough to send a signal back to Earth, and if someone on Earth was listening with a sensitive enough receiver, and if you somehow coordinated the timing despite the 3-day light speed delay, you could communicate. But the signal would be delayed. Every message you sent would take 3 days to arrive. Every response would take 3 days to return. A simple conversation would stretch across a week. You could tell Earth about something you saw, and by the time they responded to acknowledge your message, you would have experienced 6 additional days of solitude. And this assumes you have power. This assumes you have equipment. This assumes you have protection from the radiation and the cold and the absolute hostility of this environment. In reality, unprotected, you would last seconds. Not because of the cold, although the cold would kill you, but because of the absence of pressure. There is almost no atmosphere here, perhaps a few millibars, perhaps less. Your blood would not boil, as is commonly depicted in science fiction, because your circulatory system is a closed network with its own pressure. But the air in your lungs would explosively decompress. The moisture on your tongue and your eyes would evaporate instantly in the near vacuum. You would lose consciousness in 15 seconds as the oxygen in your bloodstream depleted. You would die within 2 minutes. But set that aside. Imagine you have a suit. A perfectly insulated, perfectly pressurized suit with life support and power. You could survive. You could walk across this frozen surface. You could explore. And what would you find? Probably very little. Planet 9, if it exists, is likely geologically dead. It is too small to have retained significant internal heat from its formation. Unlike Jupiter or Saturn, which still radiate more heat than they receive from the Sun, planets in the 5 to 10 Earth mass range cool relatively quickly on geological timescales. After 4.5 billion years, Planet 9's interior is probably cold and solid. There might be some residual heat in the deep core, some slow radioactive decay of uranium and thorium and potassium, but not enough to drive plate tectonics or volcanism or any of the dynamic processes that make Earth's surface interesting. The surface would be ancient, untouched for billions of years except by the slow, patient work of micrometeorite bombardment. Every few thousand years, a tiny grain of dust, a fragment of a comet or an asteroid, would strike the surface at tens of kilometers per second. The impact would vaporize a tiny amount of ice, create a microscopic crater, spray debris across the surrounding terrain, and then nothing. Silence. Darkness. Waiting for the next impact. There would be no weather. No wind, because wind requires an atmosphere thick enough to have pressure differentials and temperature gradients that drive circulation. The thin envelope of gas surrounding Planet 9 would be stagnant, still, frozen in place. Some of the nitrogen and methane might sublimate on the side facing the sun, the molecules gaining just enough energy to break free from the ice and drift upward into the exosphere. And on the night side, those same molecules might condense and fall back down as snow. But the process would be glacially slow, imperceptible on human timescales. You could walk for kilometers and see nothing change. The horizon would look the same. The surface would look the same. The sky would look the same. The only variable would be the position of the sun as Planet 9 rotated. If it rotates. We don't know how fast Planet 9 rotates, or if it's tidally locked to some past gravitational interaction. But let's assume it rotates. Let's assume it has a day-night cycle. The sun would rise above the horizon, slowly. So slowly that you might not notice the motion at first. It would ascend into the sky, a bright star among dimmer stars, and the landscape would not brighten. There would be no dawn, no golden hour, no moment when shadows grow long and the world is bathed in warm light. The sun would rise, and the darkness would remain. Perhaps if you were watching carefully, you might notice a slight increase in the number of photons hitting your suit's sensors. A statistical uptick. but not enough to see by. Never enough to see by. The sun would reach its zenith, directly overhead, and the light level would be at its maximum. Still dark, still barely perceptible, but maximum. And then it would begin to set, descending toward the opposite horizon. And when it finally dipped below the horizon, when Planet 9 rotated enough to put you on the night side, the darkness would deepen. The sun's photons would no longer reach you directly. You would be in the shadow of your own world. And the only light would be starlight. The faint, scattered photons from distant stars, none of which are close enough or bright enough to create any perception of illumination. How long would the night last? It depends on Planet 9's rotation period. Earth rotates once every 24 hours. Jupiter, despite being enormous, rotates once every 10 hours. Small, rocky planets can rotate quickly or slowly depending on their formation history and tidal interactions. Planet 9 might have a 20-hour day, or a 50-hour day, or it might be tidally locked, with one side always facing the sun and one side always facing away. We don't know, but let's assume a day of roughly Earth length, 24 hours, 12 hours of sun above the horizon, 12 hours of sun below, and the temperature would not change, not noticeably, because the sun is not providing significant heat. It's providing almost no heat. The temperature on Planet 9's surface is determined almost entirely by its internal heat and the faint infrared radiation from the cosmic microwave background. The difference between day and night might be a degree or two, maybe less, from 35 Kelvin to 33 Kelvin. Imperceptible without sensitive instruments. You're standing in a place where day and night are nearly indistinguishable, where the presence or absence of the sun in the sky makes almost no difference to your environment. You're so far from the source of light and heat that you have effectively left its sphere of influence. You're still orbiting it, still bound to it gravitationally, but in every other sense that matters, you're alone. You're in interstellar space, because the conditions here, on Planet 9's surface, are essentially the same as the conditions you would experience in the void between stars. Cold, dark, silent, empty. And yet, this is still our solar system. This is still home, in the broadest sense. This world, if it exists, was born from the same cloud of gas and dust that formed Earth. The atoms in your body, forged in supernovae and scattered across the galaxy, are siblings to the atoms in Planet 9's nitrogen ice. You're made of the same stuff. You share a common origin. But you are separated by an abyss of distance so vast that meaningful connection is impossible. Now let's change perspective. Let's zoom out. Let's leave the surface of Planet 9 and rise up, out of its feeble gravity well, until we can see it as a whole, a sphere, a planet, hanging in the darkness. From this vantage point, from a distance of a few 100,000 kilometers, Planet 9 would appear as a crescent if the sun were behind us, illuminated on one side by the distant point of sunlight, dark on the other. A thin crescent, like a new moon, but smaller, much smaller. If Planet 9 is the size of Neptune, it would have a diameter of about 50,000 kilometers. From a few 100,000 kilometers away, it would subtend a small angle in your field of view. Easily visible if you knew where to look, but only barely, because it's still dark. Even from this distance, even with your vantage point allowing you to see the entire illuminated hemisphere at once, The amount of reflected sunlight reaching your eyes would be minimal. You would see it as a faint, ghostly crescent, pale blue-gray perhaps, or brown, or black with hints of color only visible in long exposure photographs. The atmosphere, if visible at all, would appear as the faintest haze around the limb of the planet, a thin arc of scattered light where sunlight grazed the uppermost layers of gas. And around Planet 9, there might be moons. We don't know if Planet 9 has moons. Most planets do. Earth has one. Mars has 2. Jupiter has 95. Saturn has 146. Uranus and Neptune have dozens. If Planet 9 exists and is similar to Uranus or Neptune in composition, it likely captured several objects during the chaotic early history of the solar system. These moons would be small, icy, dark, orbiting in the blackness, invisible from Earth, probably invisible from anything except close-range spacecraft observation. Imagine one of these moons, a ball of water, ice and rock, a few hundred kilometers across, orbiting Planet 9 at a distance of a few 100,000 kilometers. From the surface of this moon, Planet 9 would loom in the sky, large, visibly a sphere, but dark, so dark, reflecting almost no light. You would see it primarily as an absence of stars, a black circle blotting out a portion of the star field. Occasionally, if the geometry was right, you would see the sun peeking around the edge. A bright star briefly occluded by the planet's bulk, then reappearing on the other side. The moon itself would be even colder than Planet 9. Because moons are typically smaller, and smaller objects cool faster. This moon's surface temperature might be 25 Kelvin, 30 Kelvin. So cold that if you somehow compressed the vacuum of space into a solid and measured its temperature, it would be warmer than this. So cold that the molecules in the ice barely move. So cold that quantum effects start to become noticeable in the behavior of matter. And this moon would orbit Planet 9 in darkness and silence, century after century, millennium after millennium, completely unobserved by anyone or anything. No spacecraft has visited, no telescope has seen it. It exists in a state of perfect isolation. The only interactions it experiences are the slow tug of Planet 9's gravity, the occasional impact of a micrometeorite, and the constant, patient radiation from cosmic rays that gradually alter the chemistry of its surface ice. How many of these moons might there be? 1? 5? 20? We don't know. And we may never know unless we send a spacecraft, because they are too small and too dark to see from Earth. They are below the detection threshold, lost in the noise. Now zoom out further. Let's rise up until Planet 9 is just a point of light. Let's see the orbital path. The ellipse. The long, stretched ellipse that carries Planet 9 from perhaps 400 astronomical units at perihelion to 800 astronomical units at aphelion. This orbit is enormous, absurdly enormous. If you could somehow draw it to scale, it would dwarf the orbits of all the classical planets. Neptune's orbit, which already seems vast, would look like a tiny circle at the center. A dot. Planet 9's orbital period, the time it takes to complete one trip around the Sun, would be somewhere between 10,000 and 20,000 years. Let's use 15,000 years as a middle estimate. 15,000 years. All of recorded human history fits within the last 5,000 years. The pyramids were built 4,500 years ago. 15,000 years ago, the last ice age was ending. Humans were just beginning to develop agriculture. mammoths still walked the Earth. If Planet Nine's orbital period is 15,000 years, then it has completed approximately 300,000 orbits since the solar system formed 4.5 billion years ago. 300,000 trips around the Sun, each one taking millennia, each one carrying it from the relative warmth and brightness of the inner edge of its orbit, where the Sun is slightly less dim, out to the frozen extremes of the outer edge, where darkness becomes nearly absolute, and then back again. And during all of those orbits, during all of those billions of years, Planet Nine has been alone. No other planet has come close. No asteroid has significantly perturbed its path. It follows its ellipse with mathematical precision, a test particle in the Sun's gravitational field, obeying Kepler's laws with perfect fidelity. Where is Planet Nine now in its orbit? We don't know. It could be at perihelion, its closest and brightest point, or it could be at aphelion, its farthest and dimmest. The clustering of Kuiper Belt object orbits suggests certain regions of sky where Planet Nine is more likely to be, but these are probabilities, not certainties. We are searching blind. And here's a disturbing thought. What if Planet Nine was at perihelion 1,000 years ago? What if it passed through the brightest, most detectable portion of its orbit during the Middle Ages, when humanity had no telescopes, no cameras, no ability to detect it? And what if it is now heading outward, toward aphelion, getting dimmer every year, slipping further below the detection threshold with every passing decade? We might have missed our window. We might not get another chance for thousands of years. Or perhaps it's the opposite. Perhaps Planet Nine is currently near aphelion, utterly invisible, and it's now beginning its slow journey back inward. Perhaps a few thousand years from now it will be bright enough to detect easily. But we are here now. We are searching now. And we might be searching at the worst possible time in its 15,000-year cycle. This is the cruelty of deep time intersecting with human timescales. We live for decades. We build civilizations that last centuries or millennia. But Planet Nine operates on a clock that makes our entire history look like a blink. We are trying to catch a glimpse of something that moves so slowly, on such a vast scale, that our window of optimal detection might span only a few centuries out of every 15,000 years. Let's zoom out even further. Let's leave Planet Nine's orbit entirely. Let's rise up until we can see the entire solar system. The Sun at the center. The inner planets huddled close. The asteroid belt. The gas giants. Neptune's orbit. And then, far beyond, the scattered disk, the Kuiper Belt, the region where objects like Pluto and Eris orbit, and beyond that, the hypothetical orbit of Planet Nine, a huge, lonely ellipse traced in the darkness. From this vantage point, the architecture of the solar system becomes clear. There is an inner region, warm and bright and densely packed with planets and asteroids. This is where life exists. This is where we are. And then there is an outer region, cold and dark and nearly empty, where objects are so far apart and so faint that they barely know each other exists. Planet Nine, if it exists, is an ambassador to this outer darkness, a world that exists in both realms simultaneously. Gravitationally part of the Sun's family, optically part of the interstellar void. And the Kuiper Belt objects, the distant, icy worlds whose orbits first hinted at Planet Nine's existence, are scattered across this region like breadcrumbs, each one following its own elliptical path. some taking hundreds of years to complete an orbit, others taking thousands. They pass each other occasionally, at distances of millions or billions of kilometers, never interacting, never colliding, simply crossing paths like ships in an infinite ocean. These objects are the remnants of planet formation. When the solar system was young, when the disk of gas and dust that surrounded the newborn sun was condensing into planets, these objects were supposed to be incorporated into larger bodies. They were supposed to collide and merge and grow into planets. But something disrupted the process. Perhaps Neptune's gravity scattered them before they could accrete. Perhaps there wasn't enough material at this distance to form a planet. Or perhaps Planet 9 itself disrupted their formation, its gravity stirring them up, preventing them from settling into circular, coplanar orbits. If Planet 9 exists, it is both a product of this chaos and a cause of it. It formed somewhere else, perhaps closer to the Sun, in a region where there was enough material to build a 5 or 10 Earth-mass planet. And then something ejected it, a gravitational interaction with Jupiter or Saturn, a close encounter that flung it outward into the darkness. And it has been there ever since, slowly orbiting, slowly pulling on the distant Kuiper Belt objects, shaping their orbits in subtle ways that we are only now beginning to detect. This is cosmic archaeology. We are looking at the present-day configuration of the solar system and trying to work backward to understand the violent, chaotic events that happened billions of years ago. Events that scattered planets. Events that ejected worlds into the outer darkness. Events that determined which regions would be warm and life-bearing, and which would be frozen and dead. And Planet 9, if it exists, is a survivor of that chaos. A world that was supposed to be somewhere else. A planet that should have stayed in the inner solar system, or been ejected completely, flung out into interstellar space to wander the galaxy forever. But instead, it found an orbit. A stable, if enormously distant, orbit. It remained bound to the Sun, but only barely. It exists at the edge of the Sun's gravitational dominion, where the pull of the Sun and the pull of the galaxy are nearly balanced. Now let's consider the future. Let's project forward in time and explore what happens to Planet 9 over the deep eons to come. The Sun is currently halfway through its main sequence lifetime. It has been burning hydrogen in its core for about 4.5 billion years. It will continue to do so for another 5 billion years. And during that time, it will gradually brighten. Not because it's burning hotter, but because the accumulation of helium in the core increases the core's density, which increases the rate of fusion, which increases the energy output. The Sun is about 30% brighter now than it was when it first formed. And it will be roughly twice as bright in another 5 billion years. This gradual brightening will doom Earth. Long before the Sun leaves the main sequence and swells into a red giant, Earth's oceans will evaporate. The surface will become uninhabitable. Life, if it hasn't spread to other worlds or evolved into forms we can't currently imagine, will go extinct. This will happen in perhaps 1 or 2 billion years. But Planet 9 will barely notice. Because the Sun's brightness increasing by a factor of 2 means nothing when you're receiving almost no light to begin with. At 600 astronomical units, the difference between the current Sun and the brighter future Sun is negligible. Planet 9's surface temperature might increase by a degree or two, from 35 Kelvin to 37 Kelvin. Irrelevant. When the sun finally exhausts the hydrogen in its core, when fusion shuts down and the core begins to collapse, the outer layers will expand. The sun will become a red giant. It will swell to a size that engulfs Mercury, probably Venus, possibly Earth. The inner solar system will be consumed by the dying star. But the total luminosity of the sun during its red giant phase will increase by a factor of thousands, perhaps 10,000 times brighter than it is now. And this will finally warm Planet 9. At 600 astronomical units, receiving 10,000 times more light, Planet 9 would experience surface temperatures that might climb to hundreds of Kelvin, perhaps even above the freezing point of water. The nitrogen ice would sublimate. The methane ice would vaporize. Planet 9 might develop a thick, temporary atmosphere. The surface might experience weather, wind, perhaps even rain, if there's enough water ice in the crust to melt and evaporate. For a brief period, measured in millions or tens of millions of years, Planet 9 would be a different world. Still dark, because the red giant sun, while enormously luminous, would still be a point source at this distance, but warm, active, geologically alive perhaps, if the heating penetrates deep enough to melt the interior and drive volcanism. And then the red giant phase would end. The sun would shed its outer layers in a planetary nebula. The core would collapse into a white dwarf, a dense, hot remnant about the size of Earth, but with half the sun's mass. And the light would shut off. Not completely, because white dwarfs are hot and radiate thermal energy. But the total luminosity would plummet. Within a few thousand years, Planet 9 would freeze again. The atmosphere would condense and fall as snow. The surface would return to its ancient state, frozen, silent, dark. The white dwarf would continue to cool over billions of years, fading from white to yellow to red to brown to black. Eventually, in timescales so long they're difficult to comprehend, the sun would become a black dwarf, a cold, dark sphere of carbon and oxygen, no longer emitting any detectable light, just a gravitational anchor, a mass in space, and Planet 9 would still be orbiting it, still following its ellipse, still obeying Kepler's laws, but now in true, absolute darkness. No starlight, because the sun is no longer a star. No reflected light, because there's no light to reflect. Just gravity. Just the slow, patient, orbital dance continuing in the void. How long would this continue? Forever, in principle. Orbits don't decay unless there's some mechanism to remove energy from the system. Gravitational radiation exists, but for a planet-star system like Planet 9 and the Sun, the timescale for orbital decay due to gravitational radiation is longer than the current age of the universe by many orders of magnitude. Planet 9 could orbit the black dwarf sun for trillions of years without noticeable change. But the universe is not static. Other stars exist. The Milky Way galaxy is full of them. And occasionally, over deep time, one of those stars will pass close to our solar system. Not close in the sense of a collision, close in the sense of within a light year or two. And when that happens, the gravitational influence of the passing star will perturb the orbits of the outermost objects in the solar system. Planet 9, orbiting at 600 or 800 astronomical units, is vulnerable to these perturbations. A passing star could change its orbit, could increase its eccentricity, could push it outward, farther from the sun, or could pull it inward, sending it on a trajectory that would eventually bring it close to Neptune or Uranus, where further gravitational interactions would occur. Over billions of years, over trillions of years, these random stellar encounters would gradually erode the outer solar system. Objects would be ejected. Orbits would be randomized. Planet 9 might be flung out into interstellar space, becoming a rogue planet, wandering the galaxy forever. Or it might be captured by another star, becoming part of a different stellar system. Or, in an even more distant future, the Milky Way will collide with the Andromeda Galaxy. This is already happening, in the sense that the two galaxies are gravitationally bound and falling toward each other. In about 4 billion years, they will merge. The collision will be slow, gentle by cosmic standards, because galaxies are mostly empty space. Stars will pass by each other without colliding. But the overall gravitational field will be disrupted. The Sun, the black dwarf Sun, will be flung into a new orbit within the merged galaxy, and the perturbations to Planet 9's orbit will be significant. It's likely that Planet 9 and most of the Kuiper Belt and the Oort cloud will be stripped away during the galaxy merger, scattered into the intergalactic void, lost forever. And this brings us to a profound realization. Planet 9, if it exists, if it's really out there orbiting in the darkness, is temporary. Not temporary on human timescales. It will likely outlast our species. It will likely outlast our sun's main sequence lifetime. But temporary on cosmic timescales. Eventually, through one mechanism or another, it will be removed from the solar system, ejected, scattered, lost. And if we never see it, if we never detect it during the brief window of time when humanity exists and has the technology to search for it, then it will pass through history unobserved. A ghost, a mathematical inference, a perturbation in the orbits of distant objects that hinted at something massive lurking in the dark. Future civilizations, if they exist, if intelligence arises again on Earth or spreads from Earth to other worlds, might look back at our astronomical records and see the evidence we collected. The clustering of Kuiper Belt orbits, the computer simulations suggesting a planet, the failed searches, and they might wonder why we never found it. They might develop better telescopes, more sensitive detectors, and they might finally see it, or they might conclude that it was ejected long ago, during the early chaotic period of stellar encounters that we missed because we weren't watching. Or perhaps they will find it easily, because by the time they exist, millions or billions of years from now, Planet 9 will have drifted into a different part of its orbit, a brighter part, a more detectable part, and they will look back at us and puzzle over how we could have missed something so obvious. This is the humbling reality of astronomy. We are observing the universe at one specific moment in cosmic time. A snapshot. The configuration of the solar system right now, in the early 21st century, is unique. It will never be exactly the same again. Every planet is in a specific location in its orbit. Every asteroid, every comet, every grain of dust. And we are trying to understand the entire system based on this one snapshot, this one frozen moment. Planet 9's existence or non-existence is a question that is specific to this moment in time. Either it's there now or it's not. Either it's in an orbit that makes it detectable with current technology, or it's not. Either we will find it in the next few decades, or we won't. And if we don't, that doesn't necessarily mean it doesn't exist. It might mean we looked at the wrong time, or in the wrong place. or with instruments that were just slightly too insensitive. The universe is not obligated to reveal its secrets on our schedule. Now let's bring this back to us, back to Earth, back to the present moment, back to the claustrophobic realization that we are sitting in a tiny bubble of light, surrounded by darkness, sharing our solar system with something we cannot see. Every night, when the sun sets and the sky darkens and the stars come out, we are looking outward into the universe. We see the familiar constellations, the Milky Way arcing overhead if we're far from city lights, the planets, if they happen to be visible, Venus, Jupiter, Mars, Saturn, bright, steady points of light moving slowly against the background stars. But we are not seeing our entire solar system. We are seeing the parts that are close enough and bright enough to reflect sufficient sunlight. We are seeing the tip of the iceberg, the illuminated fraction. The rest exists in darkness, invisible, unobserved. And somewhere in that darkness, perhaps in the direction of the constellation Orion, or Taurus, or somewhere else entirely, there might be a world, a massive world, a planet with 10 times Earth's mass, a gravitational giant. And it is there right now. Right now, as you listen to this, it is following its orbit. It is receiving photons from the sun. It is reflecting a tiny fraction of them back into space. And those photons are traveling through the void, spreading out, diluting, fading, until they reach Earth as an undetectable whisper. We have built telescopes. We have built cameras. We have dedicated thousands of hours of observing time to searching for this world. And we have found nothing. Not because we're incompetent, not because we're not trying hard enough, but because the universe is vast and dark and cruel in its geometry. The inverse square law is not a villain. It's not a conspiracy. It's just mathematics. Just the inevitable consequence of light spreading across an expanding sphere. But it feels like a barrier. It feels like the universe is hiding something from us, deliberately, maliciously, and we are left with scraps of evidence. Orbital perturbations, statistical clustering, computer models, indirect hints that something is out there. We are a species that evolved under a bright sun. We evolved eyes that see in the visible spectrum because that's where our sun emits most of its energy. We evolved to navigate by sight, to rely on light, to trust what we can see. And now we are confronted with a region of our own solar system where sight fails, where our eyes, our telescopes, our cameras, all of them, are insufficient. We are blind, and we are forced to navigate by touch, by feeling the gravitational influence of unseen objects and inferring their existence from the patterns they create. This is humbling, profoundly humbling. We like to think of ourselves as knowledgeable, as scientifically advanced, as capable of understanding the universe. And in many ways, we are. We have measured the cosmic microwave background. We have detected gravitational waves. We have imaged black holes. We have sent spacecraft to the edge of the solar system and beyond. But we cannot see a planet in our own backyard. We cannot detect a world that might be closer to us than the nearest star. We cannot illuminate the darkness that exists just beyond Neptune's orbit. And this is not a failure of science. This is science working exactly as it should. Science is the process of asking questions, gathering evidence, testing hypotheses, and admitting when we don't know something. And right now, we don't know if Planet 9 exists. We have compelling evidence that suggests it might. We have good reasons to keep searching. But we don't know. And there's a strange beauty in that uncertainty, a reminder that the universe still holds mysteries, that there are still discoveries to be made, that we have not mapped everything, that we have not answered every question. The darkness is still there, the unknown is still there, and it's waiting. Maybe we'll find Planet 9 next year. Maybe we'll find it in a decade. Maybe we'll never find it. Maybe it doesn't exist at all, and the orbital clustering is a statistical fluke or caused by something else entirely. Some other mechanism we haven't thought of yet. But the search itself is valuable, because in searching for Planet 9, we are learning about the outer solar system. We are cataloging thousands of distant objects. We are mapping the architecture of the Kuiper Belt. We are refining our understanding of planetary dynamics and gravitational interactions. We are pushing the limits of our detection technology, and we are confronting the uncomfortable truth that the universe is under no obligation to be comprehensible to us. We are small. We are brief. We are a collection of atoms that have organized themselves into thinking patterns for a brief moment in cosmic time. And we are looking outward, into the darkness, trying to understand our place in it. Planet 9, real or imagined, exists at the boundary of our perception, at the edge of what we can know. And that edge is not a line drawn by human limitations. It's a line drawn by physics, by the speed of light and the geometry of expanding spheres and the fundamental relationship between distance and brightness. We cannot move that line through sheer will. We cannot make the photons travel faster or dilute more slowly. We cannot change the inverse square law. We can only build better instruments, collect more data, search more thoroughly, be more patient. And maybe, if we're lucky, if the universe is kind, if Planet 9 is in the right part of its orbit at the right time, we will see it. A faint point of light moving slowly against the stars. And we will know, finally, that it's real. That the darkness was hiding something. That we were right to search. Or maybe we'll never see it. Maybe the darkness will keep its secret. And we'll be left wondering, forever wondering, about the invisible giant orbiting just beyond our campfire's light. And in the end, that wondering is part of what makes us human. The need to know, the drive to explore, the refusal to accept that some things are unknowable. We will keep searching. We will keep looking. We will keep collecting photons from the void and hoping that one of them carries the answer we're looking for. Because we are children of the light, and we refuse to surrender to the dark. Even when the dark is all there is, even when the photons die before they return, even when the mathematics tell us that some things cannot be seen, we look anyway, we search anyway, we hope anyway, and maybe that's enough. Maybe the search is the point. Maybe the mystery is the gift. Maybe the darkness, vast and terrifying and beautiful, is exactly what we need to remind us that the universe is so much larger than we are, so much stranger, so much more full of wonder than we can possibly imagine. Planet 9, wherever you are, whatever you are, whether you exist or not, we're still looking, we're still here, still staring into the void, still waiting for you to reflect just enough light to be seen. And if you never do, that's okay too, because the journey into the darkness, the attempt to see what cannot be seen, the struggle to illuminate the unilluminable, that is what makes us alive. That is what makes us human. That is what makes us worthy of the light we were given. So we will continue. into the dark, into the unknown, into the beautiful, terrible silence of the outer solar system. And we will carry our small light with us, and we will hope, and we will search, and we will wonder, until the last photon fades, until the last question is asked, until the universe itself grows cold and dark and still. We will search for you, for truth, for understanding, for connection across the impossible distance. And if we find you, what a moment that will be. What a triumph. What a testament to human persistence and curiosity and stubborn refusal to accept the limits placed on us by physics and distance and time. But if we don't, if you remain hidden forever, if the darkness keeps you to itself, then we will live with that mystery. We will carry it with us. A reminder that the universe is vast, that we are small, that some secrets may never be revealed. And that's beautiful too, in its own way. The unknown, the unseen, the invisible leviathan, orbiting, waiting, silent, in the dark, where the light cannot reach, where we cannot follow, where the photons go to die. Rest now. Let the darkness embrace you, not the terrifying darkness of Planet 9, but the gentle darkness of sleep, the peaceful darkness of closed eyes, the restful darkness where dreams live. You have journeyed far tonight, into the outer solar system, into the mathematics of light, into the philosophy of perception. And now, it's time to rest. The universe will still be here tomorrow. The mysteries will still be waiting. The darkness will still be dark. But tonight you can let it all go. The search, the questions, the wonder. Let them drift away like photons into space, spreading out, diluting, fading, until there is only silence, only stillness, only peace. Sleep well, and know that somewhere, in the vast dark, Planet 9 might be real, or it might not. But either way, the universe is beautiful, and terrifying, and infinite. And you are a part of it. A small part, a brief part, but a part nonetheless. Rest, dream, let go. The photons will continue their journey without you. The darkness will remain. The search will continue. But for now, sleep.